Now that we've taken a look at signal conditioning, let's look at how we calibrate or scale a signal once it's been conditioned. Once a signal's been conditioned, there are various types of communication protocols that differing instrumentation can use. We'll take a look at some of those communication protocols in the next module. For now, we're going to take a look at the current loop. Here you can see a signal with a range between 4 and 20 milliamps. And you can see this example is a level sensor. This level sensor uses a 24-volt power supply. You can see the wires running to the power supply. There are two other wires running to what is visualized here as a cabinet. Inside the cabinet, there's a termination block. That's where these wires are running. Above these wires, you can see a resistor. And if you look closely, you'll be able to tell that that is a 250 ohm resistor. So we'll call that the front of the cabinet. In the back of the cabinet, we have two wires running out of the back of the resistor. These wires go to the control system, and the control system can either be a PLC or a DCS, where PLC stands for Programmable Logic Controller and DCS stands for Distributed Control System. The level sensor shown here contains a sensor which transmits the unconditioned signal to the signal conditioner, which transmits a conditioned signal output, and that is the 4 to 20 milliamp signal. I want you to see that some instrumentation contains numerous portions of the system, while in other systems, the components are all separate. Here we have a Rosemount level sensor data sheet. We can see that it utilizes a 4 to 20 milliamp loop. Flipping to the next page, we can see that the range it is able to sense is from 0 to 26 feet. Now we're going to learn how to scale. So we're going to use the good old equation y equals mx plus b because this is a linear signal, where y is equal to the engineering units, or 0 to 26 feet. M is equal to the slope, which we don't yet know. X is equal to the input, we'll come back to that in a moment, and b is equal to the offset, and we also don't know that. But that's what scaling is. It helps us to calculate the slope and the offset, which will be useful when we are adding this instrument to the control system. So for the input, we're actually going to use 1 to 5 volts. And we come up with 1 to 5 volts because the resistor is 250 ohms. Using Ohm's law and 4 to 20 milliamps, along with a 250 ohm resistor, we come up with 1 to 5 volt range. This is the input we'll use for the control system. Now that we know our variables, we can use two equations to solve for the two unknowns. Doing some simple math, we find that m equals 6.5 and b equals negative 6.5. Here I've graphed the engineering units on the y-axis in feet and the volts on the x-axis. And I've drawn the calibration curve according to the data. This calibration curve gives us a set of data points that will be useful in the control system. So now you've had practice creating a calibration curve or scaling data from a 4 to 20 milliamp loop, or otherwise known as a current loop. This is only one example. We've scaled this signal for use in an industrial setting where we're using a DCS or a PLC. It might look a little different to scale a signal for a microcontroller or an Arduino, but it's the same process.